So far we have discussed two different aspects of image segmentation, or two different approaches. One was based on the image discontinuity detection, okay, or rather the pixel discontinuity detection, whereby we had obtained the boundary pixels, rather from the edge pixels we had connected them into binary pixels using the standard pixel chaining technique or using the Hopf transformation, and we also saw similarity based region segmentation, in which case we studied the approach based on thresholding, and we also discussed in the last lecture that how to choose that threshold, and we had discussed that how one goes about choosing the threshold using some optimality criteria or based on the histogram of the boundary pixels only. All right. Now, today we will be discussing yet another approach towards segmentation, and that is also based on the similarity property of pixels. Okay, and I mean, one thing which we must note again and again is that the basic objective of image segmentation is to obtain the different regions that exist in the image, and the regions normally correspond to the background and the different objects that are objects of interest which are present in the image. All right. So, I mean, our approach will be basically to extract those regions directly. So, today, whatever techniques we are going to discuss, okay, they are called as region segmentation approach, okay, because there directly the regions are obtained. As an output of these algorithms, we directly obtain the different regions. So, our topic for today is region-oriented segmentation. Now, before we go into the details of the region-oriented segmentation approach, okay, let us have some basic formulations about the region segmentation, okay, or rather some basic formulations about segmentation is necessary, okay. So, we first define all those basic formulations. Firstly, what we are trying to do in a segmentation. Somebody gives us an image, okay, and we can think of this way, that the entire image consists of one region R, okay. Let R be a region that denotes the complete image, okay. R be the region describing the complete image. And let us segment this region into a number of smaller partitions, or rather segments of the image, okay, and each of the segments are nothing but smaller regions. All right. So, let R1, R2, etc. up to Rn, that means to say we assume that there are n smaller regions or n different partitions existing in the image, okay. So that R will be divided into all these many partitions, and with this definition, all right, we can define the following properties, okay. The first thing we must have as an output of segmentation is that the union of all these regions, okay, when I have union of Ri where I is equal to 1 to n, okay, can you tell me what it should lead to? It should lead to R. So, by stating this property, what we are fundamentally defining is that the segmentation process is complete. Okay, that means to say there is no other pixel, okay, which hasn't been classified into any one of the regions. Okay, so that means to say the image has been fully divided into a number of regions. All right. So this basically denotes indicate the completeness property of segmentation. The second property which we must fulfill is that Ri should be a connected region. Let us recall the definitions of our connectivities, okay, where we had defined the 4 connectivity, 8 connectivity and all these things, okay. Now basically by calling that Ri is a connected region, it means that all the pixels, okay, within a particular region, okay, should be connected to other pixels, okay, in the same region, all right. The third property is that if I have the intersection of 2 regions, that means to say, let us take one region Ri and let us take another region Rj and let us take an intersection of this, okay, then the intersection of these two should lead to a null set, okay. So this should lead to a null set for all ij, but provided that I is not equal to j, okay. So this indicates that all the regions must be disjoint, okay. So this indicates the disjoint property. The fourth property is that if we define any similarity property, okay, for the pixels, okay, because after all, how are we going to extract the regions? Extraction of region should be based on some similarity property of the pixels belonging to that region, okay. So let us call that property as P, okay. The property P defined over the region Ri, okay. Now this property should be true for all the pixels within that particular region, okay. That means to say Pri, when I say that Pri is equal to true, that means to say that all the pixels, okay, belonging to the region Ri must fulfill that similarity property, okay. Now what is that similarity property? We will come to that. I can give you a very simple example. That similarity property could be very simply that their image intensity should lie within a particular zone, okay. That means to say we can define 2 thresholds and we can say that their image intensities must lie within that. Or let us say I specify that their image intensity should be 26 plus or minus 5, something like that. If I define, then all the pixels in the region Ri must be having, okay, pixels whose intensities are between 21 to 31, okay. That means to say that it should be the similarity property must be fulfilled by all the pixels, okay. And this property, okay, should hold good for all the different regions. That means to say when I define other regions, that means to say with I is equal to 1, 2, 3, 4, when I define all other regions, every region must fulfill this property. That means the pixel within that region must have the common similarity property, okay. So this must be true for all for I equal to 1, 2, etc. up to n, all right. Now Pri, this function P is very often defined as the logical predicate over the points, okay. So some people or some literature call Pri as the logical predicate over the points in the set Ri, okay. The fifth property which we must have is that if I take the union of Ri and Rj, okay, and on the union of these two sets Ri and Rj, if I try to see the logical predicate or rather the similarity function, okay, what do you think? Should it be true or should it be false? It should be false, okay. That means to say that two different regions, okay, must not have a very similar similarity property defined. Okay, that means to say, taking the union of the sets Ri and Rj, if I take any pixel from the union of set Ri and Rj, okay, then they should not fulfill the common similarity property, okay, because Ri and Rj have been already defined to be two different regions. All right, so P Ri union Rj should be equal to false, okay, for I not equal to j. All right, only if I is equal to j, then it is going to be true. Otherwise, this property is going to be false. All right. Now, this definition, or rather this basic formulations were necessary because when we discuss the algorithms today, okay, that time we will be again and again coming to this property, okay, and we have to refer to this in order to see that what we are doing in the algorithm, whether it is fulfilling our objective or not. Rather, you can think it of this way, that all these 5 properties which we define, okay, must be fulfilled in a region segmentation process. All right. So, we now discuss about the region segmentation approaches, okay. And we can have two distinct approaches towards region segmentation. One is what is known as region growing, okay, and the second approach is region split and merge. Now, the region growing approach is done by pixel aggregation. So, we can write that region growing by pixel aggregation. We will be first discussing about the region growing approach, and then we will go over to the region split and merge approach. So, first let us discuss about the region growing. All right. Now, to discuss about region growing, let us take a typical image, okay. Let us think of this particular grid only, and we define an image within this region. I am not drawing all the internal grids because I suppose they must be already visible by you, and I am going to write down the intensities, okay, of the pixels within the grid. All right. So, let us write down the intensities, and I write it down this way: 0, 1, 0, 0, 2, 1, 1, 1, 0, 1, 1, 0, 1, 2, 0, 0, 1, 1, 1, 2, 0, 1, 1, 2, 0, 1, 2, 1, 1, 0, 0, 1, 1, 2, 1, 0, 0, 1, okay, and now we have 7, 6, 5, 7, 5, 5, 6, 7. Let us fill up the table. This is the image that we have. All right. Now, in the region growing approach, what we do, we first we first select a set of seed points. All right. We first select a set of seed points from which we grow the region. Okay. Or rather, to the seed points, we will be appending some of the neighboring pixels that fulfill some similarity property. Okay. So we have to do two things. First is that we have to define some seed points. Okay. Seed points from which the region growing will take place. And the second thing is that we must define a proper similarity function. All right. Now, let us say that we select the seed points as follows. Supposing this pixel which I mark with green, this is a seed point. Okay. And somewhere over here, supposing this pixel is a seed point. And now, let us see the region growing. Okay. And we also have to define a similarity measure. Let us say that we define this P of Ri is defined such that all the pixels belonging to the region Ri will not have intensity difference, okay, more than 2. Okay. That means to say that the intensity, or let us say intensity difference more than 3 it should not have. Okay. Pi should be defined in such a manner that pixels within Ri must not have difference of intensity more than 3. So this is how I define the Pi. So now what we will do, we will start with the seed point, okay, and do the region growing. All right. So what we will do now, we will start with this seed. I mean, we can start with any seed, but let us say that we start with this seed. Now we see its neighbors. Okay. I mean, rather I should have indicated this seed with a different color. Let us put a blue color for this seed and green color for this seed. All right. Now, I start with this seed and examine its neighbors. Okay. Now I find that all the neighbors are fulfilling the property that Pri, I mean their pixel intensities do not exceed a difference of 3. Okay. So I club all of them together. That means to say that if I call this seed to a particular region R1, okay, then all the neighboring pixels of this must belong to R1. Okay. Now what I do, I examine the pixels which are neighbors of this grown region. So effectively now I have grown this region. I started with this pixel, with the seed pixel, and now I have grown pixels around it. Now I will grow this region further by seeing that this particular property is fulfilled. So I will be attaching these pixels. Okay. This is also a neighbor, so I must attach this. This is a neighbor, no doubt, but this is having an intensity of 7, and 7 is clearly an intensity which will not fulfill the defined property. All right. So I cannot club this particular pixel to this region. Okay. But I can always club all the pixels which I am marking now. So, through successive iterations of region growing, okay, I will be finding that all these pixels, okay, will be grouped together as belonging to the region R1. Now what we find that further to this iteration, we cannot add any more pixels, okay, to this region, isn't it? Because the moment I choose any pixel from these regions, okay, no, of course I can choose this one. But the moment I try to choose any other pixel, okay, which are neighbors of this, that means to say anything from here, okay, I find that clearly that is not possible, because that will not fulfill that the pixels within Ri must not have a difference of intensity more than 3. So my region growing process stops there, okay, and I can now take the other seed, okay, which is 7. Alright, so now I examine all the pixels, okay, which are neighbor to this particular seed, okay. I find that all of them can be included, okay. And if I proceed this approach, okay, we can clearly see that basically all of them, all the remaining pixels get clubbed into this region. So you see that the region is growing, this blue region is growing, and now again after one more iteration all these pixels will belong to the blue region. After one more iterations, even these pixels will belong to the blue region. So now what I have got from this image is that this entire image, which is R, which I can call as R, has been divided into two regions. We call it as R1 and R2. Okay. Let us call this green region as R1, okay, and the blue region as R2. Right? And what I find is that the union of R1 and R2 leads to R. If it does not, okay, then possibly a third region R3 exists. Okay, supposing somewhere here I have got a set of pixels, okay, which do not fulfill this defined similarity property, okay, then we have to go in for a third region. All right. So let us see all the different properties. Clearly the completeness property is being fulfilled here. That means to say that the segmentation process is complete for us. Then whether we choose R1 or whether we choose R2, we find that they are connected regions. All right. The third property is also fulfilled. That means to say R1 and R2's intersection is definitely going to be a null set, because both R1 and R2 are completely disjoint sets. Okay. Now PRI is equal to true for R1 and it is also true for R2. Okay. And the property number 5 was that if I take R1 union R2, okay, and define the similarity measure, obviously that similarity measure will not be fulfilled. That means to say I cannot merge the regions R1 and R2 together, okay, because they will not fulfill this fifth property. Is that understood? Yes, please.
Any questions? If there is a region,
yes,
within one of the regions which is similar to another region outside, like say there is another region R3 in R2,
okay,
which has got similar pixel values as R1.
Okay, okay, right. So I mean there is a very interesting question, and I mean I was expecting that this kind of question may be there. The question is that within this region R2, all right, we are having a set of pixels whose intensities are in this region 0, 1, 0, 1, 2, means the type of intensities with which we have dealt with in the region R1. And the question is that in that case, should we call the new region as R3 or should we call the new region as R4? I mean as R1. Okay. All right. I mean, should we call it as R3 or should we call it as R1? That is the question. Now, one thing which you find is that if you call it as R1, okay, tell me, are you fulfilling the property number 2? Property number 2 is not getting fulfilled, so you cannot call the new region as R1 once again, just because the PRI is getting fulfilled, okay, that is not enough. So you cannot call it to be the same region, rather it has to be a different region. Okay?
But then fifth property is not features. PR1 and PR3 union will not be false.
Okay, in this case it is like this, but very often the segmentation algorithms are a bit modified so that this I and J which you take, okay, they are normally taken as the neighboring regions. Okay, they are not taken as the completely different regions. Okay, they are normally taken to be neighboring regions. Okay, any other questions?
Sir,
Yes, please.
if in the first region, if a pixel point, if the pixel value is 4,
Yes, first region if the pixel value is 4.
then that will lie in both R1 and R2 regions. In which region we will include that point?
Well, the thing is that if somewhere here you have got a 4, somewhere in the middle you have got a 4, then you cannot classify it into R1 or you cannot classify it into R2. Okay? But if you are having this in the boundary, okay, then there is a problem. Okay, then it may fall under R2, then it may fall under R1. Okay, and as a matter of fact, to tell you that, let me tell you that in the boundary region, such ambiguities are indeed there. Okay, very often we encounter such ambiguities, and what happens is that the seed which is chosen first, okay, it belongs to that region. Okay, so if we choose the seed of R1, if we take the seed of R1 first, then it will be clubbed into the R1 region. But if we had considered the seed of R2 first, then it would have been classified into the R2 region. Okay, but usually near the boundaries of two regions, there are such ambiguities existing.
Should we not come on the property number 3 that there should not be any common in between Ri intersection Rj is equal to 5. If 4 is the common to both the regions, then that cannot be a point according to our rule.
No. What you have to do, you have to clearly specify. You cannot keep it ambiguous. You have to clearly specify that whether it belongs to R1 or it belongs to R2. Once it belongs to R1, you cannot say that it belongs to both R1 and R2. Okay, only if you say that it belongs to both R1 and R2, then the question of a disjoint thing doesn't hold good. But once you classify it into any one of the regions, okay, it is still, R1 intersection R2 is still going to be null set. Okay. Now, this approach looks pretty simple, no doubt, but there are two important questions which must be answered. The first question is that define seed points, and I put a big question mark over here. How do I decide that which are going to be the seed points? The second aspect is define similarity function. Okay, I put a big question there also, saying that what kind of a similarity function do I choose? Is it always true that the similarity function is based on the intensity values? May not be. Let's say, for example, we very often have images, okay, which are having a very definite textures. Okay, textures means there are certain repetitive patterns. Okay, let us say that we have some pattern of this nature. Supposing we have a pattern of this nature which is getting repeated over the image. All right, and beyond this we have got some other patterns. This is a type of image that I have got. Now, I ask you to do the segmentation of this image. Alright? If I try to apply the similarity criteria based on intensity, okay, I may land up into problem. Like, let us consider that this is a binary image, meaning that wherever I have not marked it with pen, okay, those are high intensity values. That means to say intensity value equal to 1, and wherever I have got the pen marks, okay, there the intensity is equal to 0. Okay, just a simple black and white image. Now, can I do a region segmentation or not? So very clearly, by observing this image, I can clearly see that there is a definite region here, and there is yet another region, okay, which exists over here. There are two distinct regions which are very clearly available. We can see that, okay. But if we apply the similarity criteria based on image intensity alone, okay, we will not be able to do a proper classification of this particular region, or rather we will not be able to do a segmentation. Possibly it will lead to too many number of regions, okay. Maybe that I will be getting one small region like this, and within this I will be getting yet another region, again another smaller region like this. I mean, like this I am going to get a plenty of regions if I follow the intensity based similarity measure. But in this case, the similarity measure should not be just intensity based alone. Rather, we should take a complete texture element. This, for example, this together constitutes a texture pattern. Okay, this is yet another texture pattern, and what we are looking for is similarity of textures. Okay, and that defines the segmentation. Okay, like this there are a number of descriptors. One may use in color images, one may use color as a definite clue for defining the similarity function. So one uses color, one uses texture, okay, or one can use the motion parameters. Like if it is a moving image, then one can make use of the motion parameters to define the similarity. So there could be a number of similarity functions, okay, and everything depends upon the image. Okay, I cannot always say that always the similarity function is going to be based on intensity, or always the similarity function is going to be based on texture. It depends what kind of image do I have. Now the second question is about the selection of seed points. If you select the seed points in such a manner that the region growing is possible like this, I mean possibly the way we chose the seed points, okay, we did not have any difficulty, okay. But if we had chosen, as somebody was mentioning, if we had chosen the seed point to be an intensity value equal to 4, supposing here somewhere over here I have got an intensity value equal to 4, okay, and I choose that as our seed point, okay, we would have definitely landed up in trouble. Our entire segmentation result would have been different in that case, okay. So again there should be a proper rule of choosing the seed points, okay, and if we frame a rule, we have to think about that whether it is true always to apply that rule. Now in certain cases it may be possible, like say for example I give you the example of thermal images or infrared images, and supposing the objective for us is to detect some target out of the infrared image. Normally what happens is that in an infrared image, okay, all the hot objects, okay, they appear brighter, okay, and all the colder objects, they appear darker. I mean this is a thermal image that we are thinking of. So we have an image like this, and supposing within the image, okay, we have got a target of this nature, alright, and this target is of higher intensity because clearly it's a hot object, I mean it's a hot object, so here the intensity is more. So if I choose the seed point such that the seed point is nothing but the brightest pixel, if I look at the image and choose seed point as the brightest pixel, then we are not going to have any difficulty in extracting this particular target. Okay. But in all cases it may not be possible that way. Okay. So one may have to refer to the histogram of the image. Okay. And then usually a common approach which is followed is that look at the histogram of the image. Okay. Supposing the histogram is like this. Okay. Possibly a bimodal histogram. If you get a bimodal histogram, you choose the seed point in such a manner that they are having intensities. Okay. One seed point having intensity corresponding to this, another seed point having intensity corresponding to this, then possibly your algorithm is going to work. Okay. Again, choosing the seed point coordinate is also important. Okay. For that, if you are having some a priori idea about the object boundaries, okay, possibly that helps, because if you have a priori rough idea about the object boundary, you can choose the centroid of that particular region and then choose the centroid as the seed point and do the approach. So there could be various approach towards the choice of seed points, and everything depends upon the image and whether you have a priori knowledge about the image or not. So that is the reason why this region growing approach has not become a very popular technique, because there are often situations where this region growing approach should fail. Okay. Now there is yet another approach which has evolved, and that is known as region merging and splitting approach. So now we are going to discuss the second aspect of region segmentation, okay, which is based on region split and merge. Okay. The approach is fairly simple, okay, and let me tell you what it is. There is no such seed growing or pixel aggregation. Okay. Let us say that we have an image of this nature. Let us take a square image. This is a square image, okay, and this entire region we call as a region R. Now we are required to partition this region, okay, into some smaller partitions, R1, R2, etc., etc., so that our object of interest is properly detected. Okay. Now let us have some object, okay, drawn within this. Supposing this is the object. And this is the entire image. So, what should be the end result of our algorithm? We must have the background as a region, let us call it as region R1, and the object as another region, call that as region R2. But unlike the region growing approach, okay, we do not have, like the region growing approach, we are not having any seeds, okay, from which we will do a region growing and then extract this region. What we do, given any image, okay, first partition the image into 4 equal divisions. Okay, this approach is known as a quad tree expansion approach. Okay, so you divide the entire region into 4 smaller sections. Okay, so I use the red pen to mark the 4 sections. So four equal partitions I made. Now one thing, before I make the 4 equal partitions, okay, I should have also seen something. My image could have been like this. My image could have been having just one object, absolutely no background, and a single region image. If I had got a region like this, then I must not have done such kind of a partitioning. So the very first thing which I should check is that whether for this particular region the similarity property is fulfilled or not. So that means to say that first I will be testing the similarity function over the region R, okay, and I will see that whether PR is equal to true. If PR is equal to true, then there is no point in partitioning this region further, okay. But given this type of an image, okay, obviously PR is going to be what? PR is going to be false, because all the pixels within the region R will not fulfill any similarity property. Alright. So what I do, I split up into 4 regions, okay, and call those regions as R1, R2, R3 and R4. Now I examine that, individually I examine that whether R1 fulfills that property, or R2 fulfills that property, or R3 fulfills that property, or R4 fulfills that property. What do I find? None of them are fulfilling. None of them R2 is fulfilling. Yes, very correct. R2 is fulfilling the property that PR2 is true, because all the pixels belonging to this region R2, okay, they are having similar intensity value, okay, or same similarity measure, okay, we can call that as similarity measure. The same similarity measure is there for R2, so definitely R2 should not be segmented further. R2 has been already obtained as a segment. Now what I do, all the other regions, that is R1, R3 and R4, I got PRI as false. So I should subdivide those regions further, okay. So for R1 I get 4 subdivisions, okay, call them as R11, R12, R13 and R14. For R3 I make 4 subdivisions, okay, call them as R31, R32, R33 and R34. For R4 I make 4 partitions, okay, call them as R41, R42, R43 and R44. Now I examine that for which subregions I get PRI as true. Let me write down R11. Yes or no? Yes, it's fulfilled. R12, yes. R13, yes. R14, yes. R14 is obviously a different region, very clearly. Okay. R31, yes. R32, no. R33, yes. R34, yes. Okay. Again, R43, yes. R44, yes. And only 2 other regions haven't fulfilled, that is R41 and R42. R41 and R42 we must subdivide further. Okay. So what I do now, I make further subdivisions for this. Okay. Call that as R321, R322, R323 and R324. Okay. And all of them are fulfilling the PRI property. Right? Subdivide R41. You find that this is fulfilling the property, this is fulfilling the property, this one, all of them are fulfilling. Subdivide R42, okay, there are only 3 regions which did not fulfill earlier, but after further partitioning I find that even R42 also has fulfilled. So is there any more partitioning to be done? No more partitioning is left. Now tell me, how many regions did I get? A number of them. I got R2 as a region, R11 as a region, R12 as a region, R13 as region, R31, R33, R34, R43, R44, plenty of regions are there. So did I fulfill my objective? No. Because initially only I said that I should have got this object as a region and background as yet another region. And if I had got that, then all the basic formulations which I did initially in the class, okay, all those would have got fulfilled. But right now, these are not getting fulfilled. Like, say for example, a very simple property which we very clearly find is not getting fulfilled is that if you take the union of R2 and let us say R12, okay, they are neighboring regions, and if you take the union of that, even the union of the set R2 and R12, okay, they are the property, the similarity property is getting fulfilled. Okay, so do you think that we have completed the process properly? Very clearly now. So what we must do? Yes. So far what we were doing was that we were splitting only. We were only splitting the regions into different quadrants. Wherever we were finding that the similarity property was not getting fulfilled, okay, we were splitting those regions into 4 further subquadrants. Okay, but every time we do those splitting, okay, we should also see, here we are trying to see towards the end, okay, but actually that is not the approach. With every set of splitting, with every such splitting, you must make sure that there are no other regions, there are other regions which are mergeable. If you find that there are other regions which are mergeable, okay, you must merge them, okay, form the union and make it into one full region. Like say for example, initially, during the initial partitioning, you got R2 as a region, okay. All others were not regions because they needed some further subdivision. In the second iteration, when I subdivided R1, R3 and R4 into 4 quadrants, okay, that time itself we should have seen that whether R12 and R2 are mergeable, and if it could be merged into a single region, then try to form another union of this with the other regions, and like this we should have got a combined region, okay. And only when we find that no particular region could be extracted from that particular quadrant, we should subdivide the quadrant. Alright. So in this approach, basically it is forming a tree structure like this. So if supposing this is the root node we can call as R. Okay, we first started with a region R, and then we had got 4 partitions of R. Mind you, these partitions are not based on any property of the image. Okay, only thing is that we are finding that whether the predicate PRI is getting fulfilled or not. If PRI is fulfilled, then only then we do not subdivide. If PRI is not fulfilled, we subdivide further. So what we did, we subdivided into R1, R2, R3 and R4. And in our application, except R2, all others needed subdivision. So we generated 4 children for each one of these nodes. And then out of this, we examined that which regions were not fulfilling the property, and then accordingly we generated the descendants of all regions whose which were not fulfilling the property PRI equal to true. So have you followed this approach? So this is known as this approach is very popular and is known as region, split and merge. So as I pointed out that mere splitting does not lead to a solution. Okay, we must do split as well as merging, okay, combinedly in the algorithm, so that we can ultimately distinguish the object from the boundary, and this is a very effective approach. Although, is it possible for you to point out any deficiency of this approach? I think one thing which you can point out is that computationally this approach is going to take much time, because we have to maintain a data structure, okay, whereby we can have all these quad-tree expansions, and we must have the information pertaining to the entire tree, okay. So that much of computer storage we have, and not only that, till what extent do we carry out the partitions, okay, that's also important, and especially wherever we have curved boundaries, okay, our result, okay, will not be obtained in such a simple manner. Like if I had the object, okay, like this, okay, then if you try to do the region split and merge approach, okay, it will be taking a lot of computations, because I have to do a proper approximation to these curved outlines, okay, in order to extract the regions, okay. Any questions?
Thank you.